So our next speaker is one of the freshest faculty to become affiliated. But that does not mean just because he's recently become CERIAS affiliated that he does not have a long history of very relevant to this workspace. So this will be actually my first opportunity to hear Dr. Aniket Bera also present. Welcome.
Well, thank you so much for the introduction. Definitely listening to all of you over the last few minutes, hours. I clearly feel that I need to learn a lot more from this community. So I've tried to keep this talk a bit broad level, sort of. So I work on social robotics, human behavior learning, robotics, graphics in general. And so today's talk will talk about a little bit about what we have achieved in the last many years and try to connect some dots regarding the necessity of cybersecurity research in our field. So in this presentation, we'll embark on somewhat of a fascinating and a relaxed journey into the world of social robotics, tracing the origins to the realm of science fiction in the reality of today's cutting-edge AI-based solutions. We'll also examine some of the technological advancements that have been made to make sure that these robots or social or human-like robots are a reality, as well as the collaborative efforts of engineers, scientists, designers at Purdue or even beyond. So in the interest of time and possibly interest, I will show only very high-level videos of some of the research we have done without going into any level of technical depth. But after this talk, I'm more than happy to share opinions, discuss research or other aspects of this thing. So, all right. So recent advances in AI and robotics technologies are gradually enabling humans and agents, robots to coexist, co-work, share spaces, share environments, and it's becoming more and more relevant or important for us or technologies to model human behaviors, human interactions, human motions, and human emotions for a variety of different applications. So today I'm going to talk about some of what our lab has been working on in the last few years and how we model robots to better understand us. So science fiction has been a driving force behind our collective imagination, particularly when it comes to the concept of robots. Iconic social robots in movies and TVs, where humans and robots have coexisted, like characters like C-3PO from Star Wars, who with his fluency in multiple languages, vast knowledge of different cultures, or Data from Star Trek, who possesses exceptional intelligence as well as the desire to learn human emotions, human behaviors, have not only entertained us, but also sparked the curiosity of scientists and engineers like myself. So these fictional robots have fueled the dreams of countless researchers, motivating them to push the boundaries of technology in an effort to bring these characters to life. So the influence of science fiction is evident in the design and capabilities, but also in terms of the technology aspect. So we see today's social robots getting inspired by some of these old movies, but at the same time, the latest modern AI-driven technologies. So a social robot, so what exactly is a social robot? So a social robot is designed to interact with humans and their environment in a socially aware and appropriate manner. So they possess key characteristics like ability to recognize and respond to human emotions, communicate through language, speech, naturally, and learn the interactions through them. So this is what sets apart social robots, like you see on your left side, versus industrial or other forms of more traditional robots. So these are social. So what exactly are these robots actually useful for? So social robots can, in the education sector, can personalize learning experiences, increase student engagement, support educators, and eventually, I hope they can transform education by facilitating, adapting, these interactive and collaborative learning experiences. Social robots can also help the elderly with elderly care, support patients with disabilities, and provide companionship and mental well-being, contributing to improved healthcare outcomes and hopefully eventually enhanced quality of life. Also, these robots can manage household tasks, control smart devices, personalized scheduling, serving as efficient personal assistants. There are many more applications of social robotics, but I'm going to briefly talk about some of them at the end of the talk. So the development social robots is driven by several key technologies working together, including AI, machine learning, natural language processing, computer vision, motion planning, motion synthesis. So all of these technologies work together to enable these social robots to understand, interpret, and respond to human behavior, making them effective for better interactions. Uh, Generally speaking, in terms of modeling the interactions between social robots, humans, it's very similar to how we humans interact with each other. So there's a wide range of communication mechanisms like we humans do, and a small part, a very small part, is actually the verbal or the words of a conversation. But a very huge component is actually the non-verbal communication. There is a lot of research in understanding language from a word, you know, string of words point of view, but also there's a very less emphasis or very less research when it comes to understanding this non-verbal section of work, where things like vocal patterns, speech intonations, your body language, your gestures come into the picture. So this is where our lab sort of focuses our research on, and let's see what social robots actually need to do or what they can achieve with some of these non-verbal communication methods. So a social robot, to effectively navigate amongst people in a crowd, amongst pedestrians, understanding the pedestrian motion, pedestrian trajectories is crucial. So this capability would allow the robot to move efficiently while still maintaining safety and minimizing disruptions in the natural flow of pedestrian movement. Secondly, for a social robot to interact with humans and respond to their behaviors, it must be able to learn from the human, their body language, their gestures. This obviously includes recognizing different nonverbal cues such as facial expressions, facial microexpressions, gestures, gaits, and other physical indicators. And it should also learn from, it should not only learn from what you say, the words part of your conversation, but should be in some way able to read your mind, using all these intuitive, subconscious and conscious cues which reflect on your body. So these capabilities enables robots to understand the humans better so that they can serve us, or in a more empathetic or a human-like way. And last but not least, for a social robot to create more engaging and natural interactions, it should not only learn from you, but also have the capability to respond to you in a more appropriate way. So this involves expressing emotions, expressing content, demonstrating contextually relevant behaviors that resonate with somebody's emotion or social cues. So the broader goal, what I want to achieve is we want to enable robots and these intelligent agents. And I'm not sticking to the word just robots because there are other forms of agents which we work on, virtual reality agent or agent from a motion planning perspective. So all of those intelligent agents should not only be able to understand human behavior, psychology, and intent, but also assist and enable more collaborative interactions in the future. So depending on the level of interactions, and we had 4 or 5 different ways social robots need to work in the real world, I'm going to show you some demos, some video demos of our work in those spaces. So the first one, where trajectory understanding and prediction. So the robots need to move and walk amongst people, find people in distress, find people who need help, and learn certain cultural factors. Like, when I first came to the US about 12 years ago, I realized that people keep a bit of this personal space ahead of them when they're walking, even in dense situation. People don't try to nudge around. And I'm coming from New Delhi, India, where probably the densest place on earth, one of the densest places on earth. When I'm in public transport, nobody really cares about how you bump into people, how you interact, even on a trajectory level. So those kind of cultural traits is something we are modeling in terms of density, genders, culture, and other variables. So I'm going to show you some, brief videos of where we have deployed our algorithms, our robots, into different cultures, different behavioral settings. So, the knowledge of these, so each of these robot walks and interacts with the environment very differently, understands the culture, and then appropriately responds how to go from point A to point B efficiently, but not just optimally in terms of distance or time, also bring in the reactions from the human or making it more socially acceptable, so to speak. So we have deployed our multi-agent robots in different universities and countries, especially dense countries like India and China. So taking one step back, so the unified theory of cognition in psychology talks about how humans learn, plan, and react in loops. And so far, what you saw before, motion planning from point A to point B, is essentially just large-scale intelligent motion planning, and the decisions are fairly primitive because we're looking at just trajectories. Reducing the entire human to just a trajectory is a very trivializing the whole aspect of in general social robotics, but for many applications it does tend to work. But for more complex individual level microscopic interactions with these kind of robots, we need to look at some of the other traits, social traits, cultural, rational intuitions. So when we're looking at people more on a microscopic one-on-one level. So one of the cue which people look at is body language. So humans are naturally very skilled at perceiving body language to infer the emotional state and the intent of other people. The ability is essential to for effective communication as well as social interaction. So there are several key body cues, human perceptual cues, which we use as humans to interact with people, like facial expressions, gestures, eye contact, our gaze, and many, many others. So facial expressions have been, it's very important. And there's already a wide body of work in the affective computing community, which is somewhat like an intersection between computer science and psychology. So humans can quickly recognize and interpret a wide body of emotions or behavioral traits just looking at your faces. Like a smile would indicate some form of happiness. But that's where most of the other research has stopped. So what our lab is working on is the other side, things which you cannot see on the face, right? Recent studies have shown that body expressions or body language can play a very important role in the perception of this human behavior space. And I'm going to do a quick survey right now in front of you. So they showed participants pictures of tennis players after winning or losing a match. Can you guess if player one won the match or lost the match? Who all think player one won the match or lost the match? Won the match? Okay. How many think player one lost the match? Oh, okay. Well, significantly lower. I mean, maybe one. All right. How do you feel about player two? Lost? Okay. Okay. Now let's, I mean, it will take me another 15 minutes to do the whole study in front of you. So do it in your heads, and then I'll show you the results in the next 5 seconds. 1, 2, 3, 4. Okay. I'm sorry, most of you were wrong. One of you was correct. Again, I'm sorry, most of you were wrong. The second player won the match, and so on and so forth. Okay, now let's look at these two images. Now, what do you think about player one? Player one won the match. How many think player one won the match? Almost everybody. Okay, cool. How many do you think about player two? One lost, maybe a lost. Okay. Well, it seems that most of you were 100% accurate. So this tells us a big story about why facial expressions are just one piece of the whole picture. You can look at body expressions that tell you a lot more sometimes compared to just facial expression. And that's where we sort of leverage this idea that, facial recognition, facial understanding has other security or privacy related problems as well, especially for a low stakes problem like navigation. A robot really doesn't need to look at your face to navigate, right? It can look at your body expressions, and that's good enough to remove some of the personalized factors about this. So with this information, we built an entire suite of algorithms to do socially intelligent navigation, which refers to a robot's ability to perceive, understand, and respond to human emotions while navigating through an environment. So This capability allows the robot to interact with people in a more empathetic, at the same time considerate manner. So social robots can also, and our social robots can also perform group-aware navigation by recognizing the dynamics of groups. Equipped with many sensors and algorithms, these robots can identify group formations, distinguish between group members, non-members using different social cues, and by understanding the spatial relationships and interactions in a group, they can adapt their navigation strategies to avoid interrupting ongoing conversation. Let's say you and your friend were talking and this robot feels that, oh, there's enough space, let me just go through these two people. Most people will be irritated by that, right? So to understand the dynamics of, we as humans would know that these are two people walking together, or two or three people walking together. Let's avoid these entirely. So yeah, there's a lot of work on navigation, but let's move on in the interest of time. Body expressions are just one piece of the puzzle. We need to start looking at other cues to understand this behavioral space better. So our team has also developed an extensive suite of multimodal and context-sensitive algorithms for our social robots to enhance their ability to perceive these behaviors. So these algorithms form the foundation of our robots' emotionally intelligent structures. So a suite of algorithms utilizes multiple modalities, which means your speech, your text. There are different features in the speech. There's prosody, there's intonation, the way you say things. And I always give this example from, so we're also working on a healthcare mental health problem. So you ask your friends, how are you feeling today? Now you can say, I'm feeling okay. FYI, I'm a terrible actor. So you can say, I'm feeling okay. I say, I'm feeling okay. Same content, right, in both the cases. But the way you said, I am feeling okay, completely changed the answer from something positive to something completely negative. These are the kind of multiple modalities that are lost in the text of a conversation, but can be figured out by many different features from the voice. Similarly, considering situational context into the picture, things like environment, cultural norms, relationship between the robot and the human. As the robot spends more time with the human, there is a different dynamic that evolves, and our methods are able to capture some of that. So in terms of multimodal emotion learning, I'm showing you a short video. I hope the audio works here. Oh, okay. Clearly the audio doesn't work. Okay.
I'm teaching assistant. Lasted for 9 months.
Hi there. Today I have a very special announcement. Namely, I'll be attending the convention this year.
They pretend that they are so busy with their cell phones that they're too busy to talk, or they are too cool.
So all right, these are from a popular computer vision data set, but not in a robotic setting, right? So there are many applications for this, but one thing, and we've worked on multiple of these, one thing I want to focus on today is human-robot trust. Trust is a critical issue in human-robot interactions. As robotic systems gain more complexity, it becomes crucial for their ability to be able to blend into the society by maximizing the acceptability and reliability, right? So many studies in this space have looked at how can we humans trust robot, but very few people have actually looked at the opposite problem. How can the robot trust you, trust your information? So in this case, what I want to show you is based on the human body cues, gesture cues and everything, how realistic or how well the robot can trust you in terms of your information from you. So the robot is the truster, the human is the trustee. So, we built a deep reinforcement learning-based approach that gives decision whether the robot should or shouldn't follow human guidance instead of a probabilistic sort of an approach. So we perform an affective human behavior analysis, which looks at, verbal speech cues, text cues, disfluencies in speech, hesitation, uncertainty, the different kinds of speech hesitancy cues, like something called speech repair. And I've been doing that throughout the talk because I'm scared that you people, like a lot of you folks may not be able to relate with a lot of this robotic stuff you're working on. So something like speech repair. So one example is you ask the robot, okay, I want to go to the nearest coffee machine. How do I do that? You say, take a take a left and then go straight. Now, this is what a speech repair is. You instantly change something while you were in a conversation. Things like hesitation signals, go straight and take a left. You didn't fault, you didn't say anything wrong, but these are certain cues when you say things that we need to model to build this uncertainty model of the trust. We as humans subconsciously do this all the time. We look at many keywords like probably, maybe, might be, and we build this behavioral model between humans. Can we do the same thing with robots? So, let me see. Yes, 5 minutes. Okay, I will run. So, so our results show that the learn policy can navigate in a very time-efficient manner. If they've given a task like find object AB, it can talk to people, listen to people, and try to optimally solve a problem. We have found that our robot tends to be like, if we have a very gullible robot, which listens to everything you say, versus a very skeptical robot that doubts everything you say, somewhere in between is the optimal solution about to understand what information to use, what not to use, that's where we found the best results. And because I have 4 minutes and maybe 59 seconds, I will try to breeze through the rest of the slides. So the last point is responding. Like, we talked about robot understanding called the cues. The eventual goal is to respond appropriately, right? So we've also built a lot of these algorithms to understand, to build a transformer-based network that interactively responds with body gestures. And I'm, again, going to quickly breeze past some of these. When you have, there's some, these are examples where there are certain words where, you subconsciously use your hand gestures, your body language to create certain, relationship with your listener. So we use a large visual data repository to learn some of these automatically and learn these subconscious, subtle, as well as conscious gestures, which humans do, so that we can transfer them to a robot and show you. Okay.
But I can't go out. It's been raining all day.
That's very tiresome.
Yes, it's very damp and gloomy.
And cold as well.
And the pandemic is still at large anyway.
This is a year-old video.
Together with this soon.
We will if we all do our parts.
And have a kind heart and be willing to share our concerns.
Well, ignore the scary voice when it's being friendly, but we actually worked with psychiatrists and psychologists with the medical school, and we are building an empathy robot. Of course, I can't play the audio or show the face because it's real patients, and we've deployed such our robots to these settings where we can facilitate therapy. So one thing we found out after COVID, that there is a big demand supply gap in terms of therapy in our country. And if we can use some of our tools to bridge this gap, we can do a big service to this. So we are working with the NIH and some of organizations to work on a robot assistant therapy. So, okay, so we have looked at many of these problems, whether affect response, multimodal, body language, trajectory prediction, and hopefully you saw some results in terms of whether the robot is able to trust you or not, or therapy robots or robots that make you feel angry, right? So the important part for this session, so cybersecurity plays a very crucial role in the development and deployment of these social robots, ensuring that they remain safe, they remain reliable and trustworthy, as well as eventually become a part of our lives, right? So as social robots are integrated into the various aspects of our life, they become connected to multiple networks and systems, creating potential points for cyber threats. Social robots collect and process, as you can imagine, very, very sensitive and personal data, such as facial expressions, voice recording, making data protection and privacy essential points of discussion. Again, with AI-driven decision-making capabilities, our robots may be vulnerable to malicious manipulation, requiring robot security measures to prevent unauthorized control. So obviously, social robots are a part of the Internet of Things IoT ecosystem, making them susceptible to similar risks, security risks, and highlight the need for comprehensive IoT security strategies. And last but not least, we as a community must consider the ethical implications of using social robots, but still, trying to figure out privacy, safety, and responsible use for this technology. All right, as we conclude our presentation on social robotics, it is important to highlight that the applications are virtually limitless. And in the interest of time, I'll quickly browse through. We talked about healthcare, we talked about education, but in the retail customer service industry, it could be used for information, guidance, support for customers, home automation, scheduling, security systems, smart homes, interactive toys, for education, research, accessibility for support individuals with disabilities and special needs and promoting social inclusion. And last but not least, a lot of us were talking about this just before this, that social robots can assist astronauts in maintaining their mental well-being during long duration space missions and provide valuable support in research and maintenance. So as we continue to develop and refine social robot technologies, we can then expect to discover even more innovative applications that hopefully will impact us in the next decade or so. I cannot stop this talk without thanking my wonderful students, without which none of this research would have been possible. And last but not least, I would thank my funding agency for believing in our research and paying the bills. Thank you so much.
Awesome. Thank you, Aniket.